So I want to start thanking everybody for attending this presentation. My name is Bruno Verona, and I'm here with my colleague, Henrique Reis. We are both researchers from IPT, which stands for Institute for Technological Research, an institute located in São Paulo, Brazil. And alongside Lenovo, we are also participating in this quest to turn the DNA data storage technology a reality. For this year, we select a very interesting topic, which is the status quo and maybe the next steps for the bit-to-DNA writing machines, the machines that are responsible for the writing block and the DNA data storage pipeline. So before we went to the interesting part of the presentation, I'm going to, just to give you a little bit of context about who we are. Since 2021, a couple of years ago, we have joined efforts with Lenovo, a worldwide known company, in order to, like I told you, turn this technology a reality. Our group is more focused on the writing block and as well as the coding schemes. We also have a presentation right after lunch, I believe, that Andre is showing you some results that we've been having about our codec development. It's also worth mentioning that we are a very multidisciplinary group, since DNA data storage field is a multidisciplinary challenge. So we have experts in biotech, biochemistry, computer scientists, engineers ranging from chemical to electrical specialties. So many different kind of knowledge involved in order to address the current challenges for this technology. So I'm gonna pass the talking right now to Henrique, and I'll come back at the end of the presentation with our closing thoughts. Thank you.
Hello, everyone. So before starting, I'd like to point a bit about the issue at hand, mostly for YouTube and everyone watching later. As I believe everyone knows, data has been on a exponential rise, and it is expected to reach 163 zettabytes of data, the whole data sphere. So it's been increasing really fast. And not only that, data has become really important for our day-to-day activities. 30% of all that data is considered critical or hypercritical for daily activities. And of course, at least in this projection, 60% of the whole data sphere is considered cold storage. That means that it needs to be stored for long periods of time. And with little reading activities, you access it very few, very few times. And here is just another graph showcasing how the amount of data that enterprises are generating or are expected to generate will increase so much that the amount of storage units shipped will not follow, and it will create a zone of potential insufficiency. That basically means that the traditional forms of data storage may not be enough, and that's why everyone's here to talk about DNA and ceramics and glass as alternative medias to make this increase viable. And in this whole context, DNA pops up as an alternative, and I'd like to point a little bit about what does it mean to manufacture DNA. And just like Dave, I am not a biochemist. I'm not a biologist. I'm an engineer, so I'm kind of gonna give a engineering's perspective of the whole process and what is a DNA writing machine. The whole process is based on a cyclic reaction. At start, you have a DNA base with a blocking unit, so to control the growth of the DNA. So first, you need to remove the blocking unit. That process is called deblocking. You do that by, in this case, which is one of the many methods, you do that by washing the DNA with an acid solution. Then you couple another base. You wash it with the corresponding base you want to add. You wash the DNA with another base, and it sort of bounds to the DNA fragment. That's called coupling. And note that the DNA has, the new base has another blocking unit so that it prevents further growth. And before you deblock it again to continue growing, you need to kind of strengthen the bond between the bases so that it doesn't break easily. That's what we call oxidation. And after that, you can repeat the cycle to build a predetermined DNA fragment that you want. And this here is the very first machine ever commercialized to synthesize DNA. It was made by Vega Biotechnologies, the model 280. And of course, it was released in the 1980 as the very first artificial DNA synthesizer. It, of course, didn't have a interesting throughput. It was able to synthesize 15 bases per day, but so it's nowhere near, it would equate to 30 bits of information per day. It's nowhere near what the data storage community needs, but we wanted to show it because even from the very first machine, it's interesting to see from an engineering perspective what the machine is actually made of. So you have a human-computer interface, a power supply unit controlling all the electronics, and a fluidic module that basically has a set of pressurized containers, pressure gauges and valves, and a center unit where the DNA grows. And it manufactures DNA by doing the cycle that I just showed you, kind of like flooding in reagents and washing it out with a solvent so that it cleans the center vial. And this is a 40 years later, 43 years later, this is what a modern machine for DNA synthesis that is commercially available looks like. And you can see that even though it's a lot more optimized, it still has the same set of features. So a computer over here, most likely in the back, a power plug for the electronics, a set of containers, pressurized gauges and valves. But now instead of making a single DNA strand of 15 bases, this machine actually can work with 768 different reaction sites. And in the time span of 24 hours, each of these oligos can grow up to 148 nucleotides. By doing a fair amount of mathematics, we can estimate that this machine here, which is a modern machine for biotech, is able to synthesize the equivalent of 28 kilobytes in a day, which would equate to 2.6 bits per second of writing throughput. Of course, again, this is not enough for data storage, but these machines were never meant for data storage. They work perfectly in the biotech environment. But again, you can see that the features, they kind of they are preserved over time. So the basic elements that a DNA writing machine needs is here. And the quest for DNA data storage, one of the many challenges for DNA data storage, is how to turn 768 oligos into 768 million or a billion, so that we can actually have an interesting writing throughput. And there are plenty of innovative new devices being proposed out there. Twist has been working with CMOS-based devices like custom array, and Catalog has been working with a different type of DNA synthesis, which is based on pre-made blocks, and then you connect those pre-made blocks in order to have since those pre-made blocks are bigger than the bases themselves, you just need to connect a few of them. You can accelerate the writing throughput. And of course, us from Lenovo and IPT, we have been working with a ceramic material and a set of micro-sized features to perform synthesis. But what I want to close this segment with is that for everyone that doesn't study this topic, it's important to have in mind that no matter how, building DNA is kind of a fluidic process, so you need to wash in and out solutions. So if we don't want data centers to look like industrial plants with a set of 12 inches pipes and gigantic reservoirs, we should be looking towards what we call microfluidic technology that allows us to miniaturize the whole system for DNA synthesis. And what is microfluidic technology? To put simply, it's the manipulation and control of fluids in the environment of micrometers. When we do that, of course, we kind of scale down the devices we have commercially available, so we end up with smaller footprint devices. by the nature of scaling it down, we consume less reagents. But not only that, microfluidics usually have a higher yield, so we make more with less. The whole system becomes way safer to operate because, again, you don't have gigantic 12-inch pipes running with harsh chemicals. And all of that adds up to a more sustainable operation. So we believe microfluidics is an interesting technology to have in mind when thinking of operating the DNA data storage ecosystem. And this is not just a technology that works with the academic environment. It's not it's not just for science or scientific. We actually have a set of commercially available devices out there. The first one being Illumina's flow cell. Illumina is a company that does sequencing DNA. It reads the DNA, and it reads the equipment actually consumes these chips to handle the DNA so that you can read it. And another example is Dolomite's droplet generator. Droplet generation is a well-known technique in the pharma industry and chemical industry to kind of encase the compounds and substance that you are working with. That makes it easier to handle and to preserve. So these are just two of the examples out there for to showcase how microfluidics technology is actually something mature. And once we accept the idea of using microfluidics, we have a few questions that naturally pops up. The first one being, is microfluidics suitable for industrial application? In our experience, it is. We first start, usually when you need to scale down, miniaturize a particular process, you start with a proof of concept. That's what we call the research level development, in which we build a device that proves that it's possible to be done. Then we enter the development phase, in which we take that proof of concept. Usually we need to make a few changes in order to build a working prototype in our lab. This working prototype usually requires highly specialized personnel to run it, because there's a lot of troubleshooting, but it's necessary. And once we have a working prototype in our lab, we can reach industrial level application. That's when we sort of stop looking inside the chip, because the microfluidic chip already works, and we start working on its surroundings to make it more easier to operate and increase throughput via naturally bigger set of auxiliary equipment to run the microfluidic system. And the next question is microfluidics suitable for DNA synthesis? Well, in our experience, it is. That the picture on the right shows our very first proof of concept of a controlled environment for DNA synthesis, which is here. You can see on my hand. It's a device with just a single, actually gigantic well, so that we can easily operate it, but we can reduce the well by 1,000 in its volume. And this device here is able to manufacture DNA, and it's about a tenth of the size of what the commercially available equipment usually use to handle the DNA, which is these two white transparent plates here. So yeah, it's possible to do DNA in a controlled sense. You actually have two electrical connections here and a set of electrodes here, because we electrically control the growth of DNA. And the last question, naturally, is that it's not just about making DNA, as I showed. We actually need to make a lot of DNA so that it's interesting for the data storage environment. And we believe it's also possible because of this technology, because of our micro features. We are not really bound to X and Y dimensions like the semiconductor industry has a really hard time increasing the size of processors. We can actually build bigger devices. And not only that, the way we manufacture these devices is sort of a layered method. So not only we can increase the size in X and Y, we can also stack a set of micro-sized reactors on top of each other. So this image is quite packed, but it shows over here an inlet that allows reagents to flow in, and it feeds on these serpentines. Each of these yellow lines here would be a pair of electrodes where DNA grows, and the first serpentine can connect to the second, and the second to the third. So not only we can work with micro-sized features, we also basically we are able to unlock the z-axis for parallelization. So basically, the workflow we are trying to do here is to make this technology viable. Is that we miniaturize the reaction site. This is a commercial column, standard column for DNA growth for the biotech industry, and we are able to reduce it in volume by 1,000 times, even more. Once we have done that, which we did, we can parallelize the process by building more than a single set of electrodes on a single layer of ceramics. And of course, these are interconnected, so the liquid flows in and out freely. And once we have that, we kind of stack the layers on top of each other in order to achieve massive parallelization. And here we also have a quick side note, because this ceramic was developed for high-performance electronics. So not only we can build the microfluidics features to handle the chemicals for DNA growth, we can also build the electrical lines to feed in energy, but we can also embed electronics inside our ceramics for control. So we can, by working with those three sort of aspects, we believe we can achieve massive parallelization and control inside of chips that would be the size of a smartphone. And so basically, we believe that the microfluidic tech provides a lot of high value for the DNA data storage solutions. So going to the next segment, I'd like to answer, how far are we from commercially viable bit-to-DNA writing machines? Well, this is, of course, our opinion, but we believe most of the workforce being developed is around the magnitudes of 3 to 5 on the TRL scale, which stands for technological readiness level. This is a sort of way to measure the maturity of the technology. This basically means that we have quite a few proof of concepts, just like this one, showing that it's possible to do DNA synthesis, and that it's possible to do that for data storage, but we have yet to at least publish a technology demonstrated in simulated environment. That's basically a prototype that is able to operate continuously. That's so far, as far as we know, that is yet to be publicly posted or publicly available. And why is that? Why are these bit-to-DNA writing machines not yet deployed? We believe that's because the data center requirements, we believe that's because the research level back here that sort of develops the proof of concept is too tied to the data center requirements. That basically is, we need a compatible writing throughput, because no one's going to use this technology if it has 2 bits per second of throughput. It needs to be small on footprint, because it needs to be deployed on rack-like structures in data centers. It needs to be simple and low cost. We need to actually operate it with no high specialized personnel, which is very hard to do when we handle harsh chemicals. All those requirements and more, they're all fair, and they need to be addressed on commercially available devices. But since we are yet to deploy a prototype, we believe those requirements can be kind of relaxed a little bit, so that we can run the whole pipeline, which is very complex, like Dave said. So we believe that by relaxing those requirements, we can stress test the whole pipeline and actually get valuable information. And the way I would like to put this into perspective is that imagine that device that I showed you with 768 reaction sites. Imagine that somehow we managed to turn that into 768 million. Now, by linear interpolation, we would achieve 2.6 megabits per second, which is still not really comparable to the LTO-tape, and the device would be actually massive in comparison, but that would be a success for the DNA data storage endeavor, because it would allow us to operate the whole pipeline in a continuous manner. So to generate data in DNA, store it, and sequence it later. And that's basically what we believe we need to do to push the maturity level beyond level 5, which is basically to take these proof of concept devices that are available, and there are plenty of very interesting devices with enough throughput. So we can take those devices, we sort of mount up on a rack, so that it can be operated in a more industrial sense, or in a more commercially available sense, in a working prototype. And by doing this, we would actually get very interesting data that is sort of hard to estimate, like the logistics of running DNA, of running a DNA synthesizer for data storage, how much DNA it would generate, how to sequence that amount of DNA. All of these questions are sort of related to running the whole pipeline instead of just building a working proof of concept with more and more DNA inside of it. And here's sort of an example of interesting application that we can do to do that and also generate value to the community. Here is an example from a company in France called Biomemory, where they took two historical documents, the Declaration of Rights, from I believe, from Men and Citizen and from Women and Citizen, and they synthesized those documents and stored in those capsules that Dave was talking about, I believe. They are about the size of a bullet, and they handle those capsules to the French National Archives so that it can be stored. And this is a perfect example of how to add value to the task of developing the data storage, the DNA data storage environment, because this sort of application is not really tied to how much information you're actually generating per second. Of course, it needs to be, there's a lower threshold so that you can feasibly operate this, but it doesn't really matter if it takes a week or a day to synthesize these documents. Once they are synthesized, they are basically done. That's what the French National Archives or other sort of historical documents are there for. They just need to synthesize the information and have it stored for long periods of time and actually test the data retention and the sequencing process. So that's sort of what we call frozen storage. And this is the perfect environment to develop the technology, the DNA technology. And not only that, there's a sort of a philosophy when we work with microfluidic technology that it's developed in sort of modules, submodules. So we can take those proof of concepts that are still not quote unquote perfect, that don't manage to build billions of DNA strands, and we can parallelize them. So not only we have DNA sites in parallel inside the chip, but we also parallelize the chips themselves so that we can achieve a interesting throughput for a first generation of writing machines that of course are bound for improvement, and that's normal. So before I pass it back to Bruno for the closing thoughts, I'd just like to sort of tie everything together. Basically, there are a lot of companies that have been working on the first 3 levels of the TRL scale, which basically means to develop new chips that can handle more and more DNA, and that's really important. That's basically how other companies in the semiconductor industry work. For example, they work with the task of making transistors smaller, and there's a lot of value there. But we can also take those imperfect devices that have millions of sites and automate them in a synchronized manner so that we can push to a working prototype, which would be level 6, and further into the deployment phase so that the data center community can actually envision better how a DNA writing machine would operate on their environment. And with that, I'd like to pass it back to Bruno for the closing thoughts.
Thank you, Henrique. I'm actually turning on the pointer here. I think it will be easier to show the main points that we'd like to show you here. Actually, I'm just summing up some of the thoughts that Henrique mentioned. I think the first one and the most straightforward is that in our opinion, microfluidic technology will be one of the keys, one of the pillars to make commercially available bit-to-DNA writing machines. Why? Why we think that? Well, I guess the first point is that when we start to miniaturize the process in order to enable the massive parallelization, you handle fluids in a microscopic, even nanoscopic scale. So therefore, microfluidics. The second point we want to raise here is that microfluidic, just like also Henrique has shown, can be used to produce commercially viable products. It's not something from universities, from academia. It's not something that we show only on scientific papers. There are products in the markets that were proved to be reliable. We can trust on those products. Of course, for other industries, such as the biotech industry, as well as the chemical and oil and gas industries. But we believe this philosophy also applies for the DNA data storage, for the IT industry as well. And also, we can see very promising microfluidics chips proposed by many groups. I guess most of the groups that are bringing those interesting concepts are within the Alliance. So all those information can lead us to believe that this technology will be the key for those viable writing machines, right? So, of course, there's always room for improvements to get a higher yield and throughput. Of course, we still must continue innovate on those devices so we can fully harvest the potential of the DNA data storage technology. And for the final slide here, we would like to bring the technological valley of death graph because it's very interesting to illustrate what we are thinking the current the status quo of the technology. I guess this applies not only to the bit-to-DNA writing machines, the writing block, but also for other blocks in the whole pipeline, which is when we start developing a technology, the research level, the first 3 levels of the TRL, I mean, when we have the basic principles, we propose concepts and then we prove them. Usually it's done by academia and, of course, the research groups within companies. But when we start to go to the development phase, we reach what we call the valley of death, which is a gap when we see the investments versus the maturity level of the technology before we go to the technology industry. So it's mandatory that we can pass this gap in order to make this technology a reality. As we've seen when we compare from a couple of years ago, for example, the first presentation here in the SDC, as well as maybe 5 years ago, we have seen that this gap is narrowing down. So we are each time more closer to the industry, more closer to the deployment. But what should we do right now to bypass this gap and finally deploy the technology? In our opinion, also just like in Henrique show, we should look, maybe we should not stop looking at the microfluidics chips, the heart of the machines, but as well as for what we call the surrounding of this machine. So we can build a fully functional machine that can actually be deployed. Of course, we will not harvest in this first generation of machines, we will not harvest the full potential of the DNA data storage, but at least we have a fully working device in our real data center. So we can start building the experience that will give us feedback for the further generations, and also we'll have more investments from the industry, from research agencies, funding agencies all over the world to continue and move forward in this technology. Thank you very much. I also want to point out that there were some very interesting topics that were mentioned in the presentations, both the 2 presentations right before us. I think, and it fits very well with our opinion over here, is that maybe we can analyze the features that we have with the technology proposed so far, not only for the writing machines, but for the whole pipeline. And maybe if we select a proper use case for storage, maybe we can deploy this technology already. For example, it was very surprising for us when we were interviewing some data center managers in this year that maybe we don't have to right now to get the highest throughput possible or the highest density level as possible. Maybe the minimal retrofitting will be one of the keys for deployment of this technology. A data center manager does not want to have to rebuild the facility to have a laboratory equipment and stuff like that, or highly specialized personnel. So maybe a machine that is at least automated and you don't have to maybe handle the hazardous chemicals will be enough to have a first generation of machines. So this was quite impressive for us because we were always think about the enormous, gigantic throughput and not on this minimal retrofitting feature, as well as the maybe we should enclose the technology in a black box so the data center manager don't have to worry about how it's done inside this box, but we have a fully functional data storage device. So this was very interesting to know about. I guess if we compare with a personal computer, for example, we don't have to. We also have room for improvement for the CPU, but maybe we should start looking for the motherboard. We should start looking for the power supply, for the enclosure of this computer, so we can have a first generation that will be used by the final users. So this is the main thoughts of our presentation. And of course, the Alliance is aware of that. We have, for example, discussions like this in the roadmap groups, in the interoperable interface group. The Alliance is aware of that. And also a second point before I start doing the questions here, also was raised here, is that the Alliance should be very near to that data center guy so we can harvest and we can get this continuous feedback on what features and interesting test use cases would be interesting for deployment of the technology. So just some extra comments that were not in the slides, so we can raise the questions now. Yes.
So I see that you're talking about one small miniature pipeline that you have in the lab right now with basically the ceramic substrate that you've tested, and you're hinting towards doing a prototype that is more at scale, so more like industrial or data center level. How are you envisioning the optimizations that should go in order to actually bring together that at scale machine? Meaning, it's not just going to be having replicas of the machine that sits in the lab. So have you already started looking at what kind of optimizations need to go in order to bring, like, 100 copies of
Okay, you mean the main points of optimizations that we're looking at right now in order to have a deployable solution, right? I think I'll go back to this slide here and show a little bit of our experience with other industries. It's over here. This is actually a device that was developed in our lab to be deployed in an oil and gas customer of ours. So we have understood the process. We have proposed interesting concepts, proved the concepts on the research level, then we worked on the development in the lab scale, and finally we deployed the solution in an industrial scale. And the philosophy that we took here is that we didn't have to fully optimize the process on a research level, but we have to, as fast as possible, to deploy the first solution. So what kind of features we were looking at? Especially reliability, because our customer wanted to not the optimal solution, but a reliable solution, and a safe solution, because here we were handling hazardous chemicals, which also applies depending on the synthesis technique for the DNA data storage. So those were the main drives in our development philosophy here that enabled us to deploy the solution. So I think this is also apply for the DNA data storage. Maybe we should ensure a first generation of reliable devices rather than a high throughput device or ultra high density information. I don't know if this reply answers all your questions, right?
It does. I'm just thinking a little bit about, I don't know in this particular example, if you had other criteria, like if you want to try a prototype at a data center level, there are going to be some criteria, like not just space, there is going to be a height criteria, there's going to be a weight, there's going to be an amount of power, etc. criteria that you need to take into account. in order to just deploy it over there. And that's why I said it's not just bringing together those existing lab machines.
Yes, we have to look at a system level, the whole system, not just the equipment. Yeah, I think we fully agree with this philosophy, right? And this is what we did in this example, and we think it must be done in the DNA data storage pipeline.
Questions on miniaturization, especially since you're using microfluidics, you're going to have to fit into the limits of fluid dynamics limitations, your fundamentals. So what is the level of miniaturization you can achieve? You're showing you went down to 75 micrometer. Can you go further than that for your well size, but also for your fluidic channels? What are the limitations you see, especially for the liquids you're using right now, right now?
I think that actually depends on many aspects. Oh, okay, sorry?
Repeat the question.
Oh, yeah, sorry. You mean you want to know what are the limits of the microfluidic technology when we are handling fluids, and what are the, I guess, the limits that are actually imposed by the physics of the synthesis process, right? That's actually a good question. It actually depends on the process itself. There are multiple synthesis processes that you can do, for example, the chemical and the enzymatic system. There are indeed physical constraints that we have to take into account when we are miniaturizing the process. Of course, we cannot miniaturize indefinitely. Maybe we can reach interesting synthesis reaction sites on a nanometric scale, but this is an open question in the development the ecosystem. I think we don't know exactly an answer yet. We know that it's possible to operate in a nanometric scale. But also, just like he told you, when we start reaching this possible limit, we can also parallelize the devices on a device level, not only on a single chip level.
And to add to your question, I believe you were talking about the constraints and the kind of sort of the physics of the microfluidics. If there are limitations or actually, I would say that actually the microfluidics behaves, the reagents used behaves really well in microfluidics because we can sort of in a segmented way perform each of the processes. The chemists use the mixing of reagents and sort of handling and dosing the amount of reagents we are actually going to input inside the reaction site. We can do all of that in the same chip, in the same ceramics that we build. It's just in another section. So we handle and prepare all the reagents, and by pressure we just let them flow in. And since they have very low viscosity, at least the ones the methods we are using, it sort of flows in really easily. So it delivers all the chemicals in and out of the reaction sites.
Thank you.
Have you done cost projections at scale? And if so, I'm curious where you think the costs are at the moment.
That's an excellent question. Usually all the directors, the first question is about costs. He mentioned if we're looking at the cost. Yeah. But we do not have a proper answer yet. But to have a deployable solution, this is also came up when we were talking with data centers managers, is that cost will be one of the requirements that we should start looking from the beginning. Maybe cost, sustainability, and this minimal retrofitting, rather than just high throughput. But this is an excellent question. Unfortunately, we don't have the numbers yet. Sorry.
So, this is single-base synthesis using cross-parameter chemistry from Chelsea. Does that use acetonitrile in the process?
Yes, it does. In our case, we are using the chemical route, so yes, it does.
So, have you thought about the scale of acetonitrile required to really run this and the disposal of that level of
That is an excellent question. He mentioned about some hazardous chemicals that were involved in the synthesis, and what is the impacts when we scale the process up. This is something that is still an open discussion. We understand that since we have multiple ways of synthesizing DNA, maybe for the first generation, which is not fully parallelized process, maybe we can use a first use case. I guess this went the approach of selecting the proper use case. We can select a use case that handles a minimal amount of material, and then on the following generations of machine, maybe we can move to the enzymatic process, so we don't have to handle so many hazardous products. So,
and to add to your question, yeah, we talked about phosphoramidite method because it's sort of the gold standard for biotech, but the device itself is completely capable of handling enzymatic processes alike. So it's just a matter of develop a prototype so that we can test how much acetonitrile it would actually consume, but most likely we would sort of route out of acetonitrile into the enzymatic process, which we are also developing.
Perfect. So we can build the experience on the chemical process, which is a solid process, and then we can move to newer innovative process such as the enzymatic one.
Any more questions? I believe there were quite a couple.
Do you envision the writing mechanism being separate from the data set? Because the data set
Yeah, I believe the first generation of the he mentioned about he was sorry asking about if the machine will have separate writing and reading blocks, reading hardware. I guess in the first generation, yes. Maybe in the next 5 years or maybe the next decade, we can couple the reading and the writing blocks in a single hardware device. I guess this would be the idea and the most straightforward development roadmap of the technology, but not under the first generations, in my opinion.
And to add to your question, I believe you were talking about deploying the writing machine inside a data center. The conditions of the data center are not a problem, at least related to chemical synthesis, as far as we know. And not only that, since we are working with a microfluidic system, that this whole module here, even though it's obviously larger than a rack of LTO tapes, we can actually have all the chemicals and the DNA manufactured in a controlled atmosphere within the equipment. So it wouldn't be really an issue of at least humidity. In terms of temperature, we don't really think that the temperatures that the data center runs is actually a problem.
I guess not a question, but just a point on the previous note. Like when your writer and reader, as well as the storage, these are all modularized. It also gives you a flexibility to, increase either only the number of writers or only the number of readers, depending upon what is the actual throughput that this application might use.
Yes, this is an excellent point. She was talking about the advantages of having different hardwares for reading and write, which is the flexibility, right? You can, it's not a bad thing necessarily. You can harvest interesting features when you have different hardwares, separated reading and writing blocks. This is a good point.
And that's why the sort of reflection that I was giving about building a writing machine that has interesting throughput, but actually is larger than a traditional LTO tape. Of course, we want to make that smaller, but since we can transport the DNA outside of the machine, we can store on really small features on the imagine the DNA shells, the DNA that Dave talked about. The writer can be larger. Of course, it's better for a smaller one, as small as possible. But but the dimensions are not really an issue, we believe, at least for a first generation, of course.
Just to the point around raised about the volume used. So your 75 nanoliters, let's assume you get the 0.75 bits per base, which is something you're putting in. That's about 10 and 20 tanker cars of acetonitrile per terabyte. So, you can have that question like, what kills things in that valley of death is when your VCs run that
Yes, this is an excellent question as well. He mentioned about, based on these numbers, we still don't have a proper conditions to deploy, right? When you have to handle a lot of hazardous chemicals in order to get an interesting throughput, basically for any use case, right? So that's why the technology is not deployable yet. So we still have to work on that. So I guess this is the main idea here. But if we focus on stuff like that, maybe we can accelerate the deployment and to break that gap between research and deployment phases. Thank you. Do you have any further questions? Thank you very much.
Thank you.